So, ladies and gentlemen, we are ready for another expert talk about wideband gap and the GaN devices. And we, as usual, focus to the past articles in my magazine. And we are proud that this talk has come to a nice regular event in industry now. And the people, especially design engineers, benefit from being able asking questions direct to the experts. Okay, we can start with the first question. Here is the question coming. It's addressed to Infineon. What are the new features and benefits of the ICE driver second ADI generation 2 family of dual channel isolated gate driver ICs?
Hi, Bodo. Hello, everyone.
Hello, Diogo.
Yes, it's a pleasure to be here with all of you. Yes, I will take that question. Thanks to the audience for bringing that up. Indeed, so we launched the second generation of dual channel isolated gate drivers, and compared with the first generation, we have now new features, including dead time control. So it's possible to set that time from 10 nanoseconds up to 1 microsecond period. So this is one new features, and also there is shooter protection. So basically, in these dual channel drivers, if this feature is enabled, it also prevents that both channels, for example, in half-bridge configuration, turn on the MOSFETs or the GaN amps, and then preventing a shoot-through. Yeah, so these are two of the key features that we are bringing up. And we also made some improvements in terms of startup time. So we shortened startup time of the driver. And yeah, so we also implemented some fast active clamping that allows let's say the user to operate the driver safely, for example, in a bootstrap supply, right? So instead of using a bias supply, if some customers like to use bootstrap configuration, so this driver also allows really to have a safe operation in bootstrap mode. Yeah, I think these are in the end the four main features of the latest generation of dual channel drivers.
Thank you, Diogo. Any questions, comments from the speaker side? If not, we continue with the next question. The question is addressed to Alex. You claim GaN is more reliable than silicon MOSFETs. Why do you believe that?
I think it starts off with the fundamental point that wide bandgap devices in general have a stronger chemical bond between the constituents in the crystal. So gallium nitride, is a much stronger crystal, which makes it less vulnerable to temperature effects. But secondly, is that gallium nitride power devices, the way a lot of people make them, like EPC, the primary active elements are all native crystal elements. So you have gallium nitride, aluminum gallium nitride, and in various heterostructure layers. And therefore, you don't have a lot of issues of interface states like you do in, for example, a silicon carbide device with the oxide gate, or a MOSFET with an oxide gate that traps charge. What this all translates into is that the wear-out mechanisms in gallium nitride not only are extremely mild if you design the device correctly, but they typically have a negative temperature coefficient. So as things get hotter, the device actually performs even better.
Thank you, Alex. Any points from the presenters? Then let's continue with the next question. It's addressed to Navitas. What other 140-watt USB-C solutions and sizes exist in the marketplace today?
Okay, yeah, good question. There's a few of them, a few products out there, mostly from we have a few from our friends at Apple. We have a 96 watt 1C, that's about 185 cc in size. And then they have their latest, Apple has their latest product, a 140 watt 1C, which is around 210 cc. There's a few other, Lenovo Yoga has a 130 watt 2C, which it comes in around 155 cc. And yeah, those are to name a three. And then the one in our article, of course, which we show using this latest PFC plus AHB topology, all GaN based, that comes in at basically about 110 cc. So a dramatic reduction in size versus the existing products on the market today.
Thank you, Tom. Any things to add or put questions into it from the presenter side? If not, we continue going to the next question. It's again a question to Infineon, to Diogo. Can I drive GaN HEMTs with these new gate driver ICs?
Yes, it's possible. Actually, with these drivers, and that's also something that we describe in the article, we can drive silicon MOSFETs, silicon carbide MOSFETs, and also GaN. Of course, GaN, we see quite a lot of, let's say, variety in terms of the AMP itself or the gate structure. So therefore, it could require to use, for example, negative gate driving to avoid return on with some kind of switches, and others not. But in the end, we can implement what we call a universal GaN driving platform, and that's also what we show in the article. There is one evaluation board available in our website, where basically it's possible to configure the gate driver together with a bias supply, and then an interface between the driver and the gate of the switches, what we call RC circuit, basically, that can be configured to drive GIT gate, for example, from Infineon, or Schottky gate from other vendors, or even a cascode GaN. So it's indeed possible to do it. And we describe also that in more detail into the application note of this evaluation board that is called eval 2EDP of bridge GaN. So if the audience is also interested, you can also have a look, and there we describe in more detail how to do it. But indeed, it's possible to drive GaN also with these gate drivers.
Thank you, Diogo. Next question. It's again to Alex. Is JEDEC qualification testing adequate to guarantee device will work in my application?
We can have this discussion.
So I think that the JC70 committee is trying very hard to adapt qualification standards to new materials, silicon carbide, gallium nitride, and they're doing quite a good job. In general, I think qualification testing has its limitations. And at EPC, we've advocated this test to fail methodology to understand the true failure mechanisms. So I think that if you have qualification testing, which is in essence is a pass fail with a certain number of units that you test at one testing point, it really needs to be supplemented with an understanding of what are the fundamental failure mechanisms and how do they behave under all operating conditions. And that way you can build a true understanding of your device under any mission profile. We've been doing a webinar series. There's one today, as a matter of fact, on reliability in actual real-world applications. Today's on DC to DC converters. And we look at what are the real effects of, for example, ringing on the reliability of the device, or short circuit current periodically occurring across the device, and that understanding is critical to supplement any qualification testing. If that understanding isn't there, then there is no mission profile that is completed by just qualification testing.
Thank you, Alex. You're absolutely right. I remember something from the past when I introduced IGBT. I was called to a customer who claimed very badly that the IGBT failed. And the problem was the incoming testing technician had a new tester and tested the leakage to the maximum of the data sheet by running the blocking voltage to something wide above the rated value. So they blow up the devices, but they still had some good devices and asked me, how can I guarantee that they are always good and when they put them into their application? And I said, only God knows. So
I'm sure the customer loved that one.
But first, nobody understood the problem, and the management people were starting fighting to each other, and then they dropped it to me, to the application man, and I said, before something, I need to talk with the people and understand what they did. And we were sitting on a round table, and I had the test protocol and were reading step by step through the test protocol and asked the question. And at the end, they looked at me and they understood what they did. That happens. So yet I cannot guarantee that an application runs. That was just my adding story from the past. It had happened nearly 30 years ago. And so we can go for the next question. It's to Navitas again. Tom, what design innovations have you made to enable such a small size?
Okay, good question. Well, the design that's presented in the article is a 140 watt PFC plus AHB. So to get it to that small size, we first need to have a very high efficiency. So we need to choose topologies that can get us good efficiency numbers. So on the PFC stage, Everybody knows the standard CRCM PFC topology. This has an additional innovation where we have our GaN sensing. We have our internal current sensing feature inside our GaN IC. So that removes the external current sensor, which gives a slight efficiency boost to the system. And we've also implemented a boost follower circuit. By adjusting the DC voltage according to the AC input voltage level, we can reduce the negative current levels. We can reduce we can increase the duty cycles, and we can reduce the core loss. So that's what's been done on the PFC side. And then on the DC to DC stage, which is the asymmetrical half bridge topology, that works like pretty much during steady state, like an LLC stage, which we all know also is very efficient. We can get up to efficiency levels of say 97% for that stage. So with all of that combined, then that also includes GaN sensing on the asymmetrical half bridge stage. So we can eliminate the current sensing resistor there as well, which can give almost, half a point of efficiency boost just by removing that current sense resistor. So putting it all together, we can reach efficiencies that are greater than 94% for that circuit, which is necessary to bring it into that small size because we have to deal with the thermal issues. And then to shrink the magnetics, we had to push the frequency higher. And we also all know, we can attribute that to GaN. GaN enables us to switch at these much higher frequencies. And especially that asymmetrical half bridge stage, it's all soft switching. So there's no limit to how high we want to go with that frequency, just limited by, however high that controller can go. But basically we push that frequency of that stage up above 300 kilohertz, which reduces the transformer size. We also increase the PFC switching frequency up to about 150 kilohertz, and that reduces the PFC inductor. So putting that all together, efficiency, reducing the size of the magnetics, and increasing frequency, and of course using GaN together with our current sensing features makes for a great, high efficient and compact size.
Thank you, Tom. Any additional questions to the subject? If not, we continue to the next question. Okay, it's going to Infineon. Diogo, what's the maximum switching frequency possible with these gate drivers?
Sure, good question. Actually, these gate drivers, let's say the PWM signals goes through the isolation barrier that is implemented with Infineon's cordless transformer technology. And this modulation operates really quite high frequency, let's say. I cannot disclose the numbers, but we proved, and actually that is also shown in the evaluation board that we have in the article. So we can operate GaN at 2 megahertz without any issues, and we also have results showing that. So I don't want to say that 2 megahertz is a limit, but at least up to that range, we proved that we can reliably operate GaN in that high frequency. I think basically in the data sheet we state a range up to 10 megahertz, but yeah, actually we don't have customers requiring to switch switches so fast. So normally they are more in the 3-digit kilohertz and into the megahertz is 1 megahertz. I think that this is more or less what is now being designed in the current projects.
Okay, thanks. Another question is coming up. Again, Alex, since GaN devices are so small compared with silicon MOSFETs, Does that mean they are operated typically at higher temperatures? Does that reduce the lifetime?
So, GaN devices are much smaller than silicon devices, but they are also much more thermally efficient coming from EPC. And that has to do with either our chip scale package, which can cool from all sides, or it comes from our PQFN that has backside cooling of a native silicon substrate. So first you start with lower thermal resistance. That lowers temperatures. Secondly, you start with not generating as much heat. And, GaN devices are 10 times faster than silicon, so the switching losses tend to be much, much lower. And of course, they're much smaller, which means that you get less on resistance for the same size, or you have a much smaller die with the same on resistance. So really what you can get out of this whole thing is the same operating temperatures as you would with a MOSFET with about 10x power density. So that's, I think one of the big values of GaN. And the other thing, as I mentioned earlier, is GaN tends to operate very comfortably at high temperatures with negative temperature coefficients to the key wear out mechanisms.
Thank you, Alex. Here we look for the next question. It's addressed to MinDCet. Could the gate driver influence the reliability of the GaN power stage? That's going to Mike.
Yeah, thank you, Bodo, and good afternoon and good morning to everyone. That's a good question. Previously, we mentioned, or Alex mentioned indeed, that the JTAG testing is limited. In other words, you have to look at the application and what the user is doing in the application. And in the end, you can build as good as a GaN as you can. The user is still able to break it down if it doesn't use it correctly. And I think indeed there is a correlation between the gate driver as well, because your gate driver also has a certain control over the power stage, on how fast it can switch, on what kind of voltage it applies to the gate. And of course, all that needs to be within limits and the let's say the reliability limits of your GaN device. And I think a special caveat to be aware of is what we like to call bootstrap overcharging. So if you have even a minimal amount of DC link inductance in the source, which you'll always have because there will be a physical connection between the DC link capacitor and your source of a half bridge, for instance, there will be at some point a negative undershoot. And this negative undershoot is added to your bootstrap voltage. Now, in long terms, or long story short, that will create or can create an over voltage on your bootstrap capacitor. And if you don't do anything to mitigate that, you will get an over voltage on your gate as well, which could lead to a reliability issue on the longer term, or even on the shorter term if it's a higher voltage. So our gate driver, for instance, has mitigated that in an elegant way by implementing floating linear regulators, such that the gate voltage is always very well defined. There are less elegant ways to do it, like burning the excess voltage in a Zener diode and so on, which is temperature dependent, and in the end you're burning excessive power, which is not so elegant. But yeah, there is a strong correlation between the gate driver and the GaN power stage. There's a synergy going on there, and that needs to be right. So I would say yes, clearly there is a way to influence the reliability with a good gate driver in a positive way.
Thank you, Mike.
You're welcome.
So the question goes to Infineon. During PCM Europe 2023, Infineon introduced 600 volt GIT and 1200 volt SiC Schottky diode based Vienna rectifier and multi-phase DAB. What's the reason behind this proposal? As this PFC topology is unidirectional, so it's not feasible for bidirectional OBC PFC stage for V2X? Plus, what will be the power density of that OBC demonstrator with casing? I hate in questions these shortens, but I think Diogo knows well what the shortened sentences in the question represent.
I believe this question is about a reference design that we had in our booth, and this was featuring a 10 kilowatt per liter power density in that design. So this was in the DC-DC stage. Indeed, was a stacked dual-active bridge with GaN. In the PFC stage, actually, I'm not sure what was implemented there, but headline in terms of power density, and I think that was one of the fundamental questions, was what we target is 10 kilowatts per liter with that implementation. Of course, with a case around, because what was shown then was open. It can go down, but should be in the high single-digit power density. Yeah, would be my feedback. If you have more interest about to know more about this solution, please drop me one email. We can have a call and sync up afterwards.
Diogo, that was just my thought. It was so specially to something from your booth shown at PCIM that the people who requested that should come directly to you and have a one-to-one chat by email.
Sure, I will be glad. Thank you.
So we're looking for the next question.
Okay.
Hi, Alex. It's again for you. Can these models for GaN FET wear out to be applied
Yeah,
to
one
my
thing's also
motor
subject.
drive application?
Yes, so the answer there is yes. It's not a simple answer because motor drives have quite a variety of conditions, both often having high overcurrent conditions, lots of ringing, short circuit conditions, lots of starts and stops, which tend to temperature and power cycle the device. So it is probably the most complex mission profile for a power device. EPC has developed models for all of the various conditions, temp cycling, power cycling, and we've published most of them in our phase 15 report, which is online. We have a phase 16 report that's coming out in a few months, but also we're doing a specific webinar on motor drives and how to apply the wear out mechanisms to motor drives. It's in August, I think around August 23rd. So go on our website and take a look at that. But we do look at the various mission profiles for motor drives, and it really is quite interesting to see how the various wear out mechanisms add up to give you a prediction of not the device will or will not work, but how long will it work in your application? Will the motor drive in an e-bike last 15 years or 20 years or 2 years? And we can answer that question now.
Thank you, Alex. So the next question is going to Navitas again. Tom, usually EMI is a concern when frequency and switching times are increased. How did we solve EMI with this design?
Okay, that's a great question. We get asked that question quite frequently by a lot of our customers that are starting, their first GaN designs. They're a little bit hesitant to move the frequency up and to increase the switching speeds. They're nervous due to these EMI concerns. So You know, we've worked through a lot of those issues over the years with our in-house system experts. A lot of learning has gone into many of these different charger designs. Some of the few lessons learned include, you know, you need to include shielding, a shielding layer inside the core, inside the windings. It's always good to have, you know, additional winding in there, or if it's a planar design, to have additional PCB layer in there that is at the either ground of the secondary side potential or the ground of the primary side. There's different techniques there. Layout, of course, is very key. It's, you know, there's good practices. You don't want to be placing your, for example, AC input connections very close to the GaN device. You know, the device that's doing the fast switching, because sometimes the noise can just jump right across your filter right to the input, and you have your filter there, you think it's doing something, but it's actually not, because of the near field coupling. So you have to be careful with the layout, and also the orientation of the filter components. That also plays a role. You can get different results if a filter is rotated 90 degrees in orientation, you know, because then it can either be more susceptible to E fields and B fields inside the circuit. And then also a lot of the designs to solve additional shielding for radiated EMI, you'll have a copper shield around the unit, or partially shielded. That does two things. It helps to shield the radiated EMI, and it also provides additional thermal heat spreader around the product. So, you know, it's not just one thing. I mean, we also offer on our GaN chips, we offer programmability for the switching speed, so that the engineers like that, to be able to tune it. When they have the design on the bench, they can slow down the switching speed slightly and get a different EMI profile. Yeah, so, you know, there's a lot of tricks. You got to follow all those practices very carefully. And you also want to do it up front in the design cycle. You don't want to just build your power supply and go for the smallest size and, you know, all the other benefits we talked about, and then deal with EMI later. That can actually turn into a nightmare, and you have to throw cost at it, or do a big rip up and redesign, and your schedule's at risk. You want to really take care of this up front in the design. Get your layout as good as you can, and the proximity of the components, and, you know, basically follow all those good practices up front.
She was last week.
Could I just add something to that? You know, Tom, you talk about these practices, which are all very, very good practices in design, and they're true for you know, MOSFETs as well as GaN. But GaN has some fundamental advantages. First of all, by being much smaller, you have a much smaller layout, which tends to have less of an antenna effect. It's easier to shield. Secondly, is there's no reverse minority carrier diode in a GaN device, so you don't have the reverse recovery of a diode, which is one of the largest EMI generators in a hard switch circuit using MOSFETs. So you get rid of some of the fundamental elements that generate the EMI as well. So GaN has a basic advantage. If you can make it work with MOSFETs, it's quieter with GaN.
Yep, good point. Also, the GaN, the large tab in the GaN package is also the source. So that's fundamentally more quiet versus a MOSFET, which is the drain. So you can use a large heat spreader on the PCB and not worry about, you know, radiating more noise. So all good points.
Thank you, Tom. Thank you, Alex. It's again to Infineon, to Diogo. Why did you reduce the under voltage lookout startup time and implemented a fast active output clamping in this new generation of gate drivers?
Okay, so this is really excellent question. Can I share my screen maybe briefly, or?
Of course.
Yeah. Okay, I think it's the function is disabled. Ah, okay, now it's possible. Good. Yeah, because I think a picture says more than 1,000 words. That's why it would be nice to share the screen. So in the article we have in this figure, we try to explain and make a comparison. What is this about? What is the advantage of having a fast startup time? And actually, we implemented this in the second generation because there was a specific customer really asking for this. Yeah. Here in the first picture, you see the PWM signals in green and the yellow coming for the high side and for the low side. Let's think about the off-bridge, right? Imagine that you are supplying the high side with a bootstrap. A bootstrap voltage is this one here in red, right? So it's already stable here at this level and already above the under voltage lockout driver, voltage of the driver. But let's say the high side is only starts operating here at this point when you see the blue starting switching, which means that the driver took all this time until startup, which means 15 high side pulses of the driver and the switch were not provided, let's say, to the switching node. If you think in a LLC, it could lead to imbalance on the switching node and a very difficult startup of the system, right? This is not from our first generation. Actually, this is from a competitor part. Yeah, in our second generation, we have around, if I'm not mistaken, three microseconds. So now in the second generation, we even reduce it further the startup to 1.7, 2 microseconds in this ballpark. And in this situation, you see that then the high side gate basically gets already a signal very, very fast. Yeah, you see here, in this case, 0 switching high side pulse is skipped, right? So you can then operate the LLC with bootstrap without any problems and really start up very, very fast. Yeah. The system. So this is about the faster under voltage lockout startup time. Other thing that is also important, and that is a feature that we also describe here in these sections, is fast active output clamping. I think was also part of the question. And we also compare here situation without having this feature, what we also found in, let's say, a competitor device. So basically, without having active output clamping on the high side of the gate driver, without having that feature, if the driver is not yet supplied because the bootstrap voltage is not reached under voltage lockout level, during all that time, the high side gate is inducing, let's say, there are some voltage induced there due to Miller effect on the high side gate, and then this could lead to turn on of the high side switch. Due to this induced voltage that should not be there because the high side driver is not properly supplied, yeah, due to the bootstrap that did not yet reach the level. With this driver in the second generation that we have here, basically there is a very strong output clamping, which means the gate of the high side switch is really clamped to 0, and therefore the driver just starts operating when the under voltage lockout is activated, and that only happens here. So which means that really the converter starts operating here in a, let's say, stable and reliable condition. Yeah. So this is also a benefit that we implement, and a feature of this second generation of products. I hope this helps basically to explain.
Thank you, Diogo. I think your explanation should be clear to the people who asked that question. And we're ready for the next question. It's going to Tom. Does Navitas have a plan to take advantage of topside cooling package like Infineon QD-Pack, DD-Pack for GaN IC products?
Yeah, we don't really see those type of packages for mobile and consumer. but my understanding for the higher power and for industrial type applications, yeah, the answer would be yes. We are looking at some of the other top cooled products where it's more convenient to attach heat sinks and to do the thermal management.
Okay, Tom. That's a good forward-looking statement. So we can have the next. That's to Infineon, to Diogo again. Could you please explain how an electrical overstress in the power stage can occur and the potential impact on the gate driver IC?
Yes, I can try to explain. Again, would be nice if I could share my screen. Yeah.
Okay, of course.
You don't mind. Okay. So actually, we also addressed that point in the article. We have this section, robust isolation to electrical overstress. Maybe I make it a bit larger. So if we think about half bridge, and then we have the gate driver with the two output stages. Imagine in a worst case situation, what could happen if the drain of the MOSFET gets connected to the gate for some very special reason, okay? It would mean that the DC link would be connected to the, let's say, output of the gate driver, and the energy stored here in this capacitor would have then to flow and would go into the output chip of the driver. So in this case, the voltage would be well above the limit of the driver itself, and therefore it could destroy this chip. And what does it mean, the robustness to electrical overstress is, can or could the isolation between the input side or the low voltage side of the driver and the high voltage side be compromised due to this? I think this is very critical because in particular, when you're talking about reinforced isolation gate drivers that are placed across the isolation barrier in a power supply. Imagine, for example, in a server power supply, you have the PFC stage, and then you have the high voltage DC-DC stage, and there is the transformer that is providing the isolation, and the driver is, let's say, parallel to the transformer, also providing the isolation between the controllers and the power stage. So in any situation, this isolation can be compromised, and therefore we also performed some tests with our gate drivers, replicating exactly the situation. So basically, we did with a test setup, we really connected the DC link to the output of the driver, and of course, we destroyed the driver. And after this, we performed what we call iPod test. So it's a test that checks the isolation between input side and output side of the driver. And basically, in all tests, it proved that the isolation was never compromised. So because actually in this case, our chip, let's say the isolation element is on the input chip. So the isolation is never compromised because the input chip is always protected. So indeed, even if there is a destruction of the output chip due to electrical overstress, the isolation is never compromised. And we also show some measurements here in terms of currents, what can happen inside the driver. You see here big currents that can go really up to 600 amps. We saw this in the test. Of course, this very, very high current for a very short period of time. It will, in the end, destroy bond wires and damage the chip, the output chip, but let's say the input chip is not compromised. So the isolation stays in place. Again, sorry, this is a bit complex topic, but I hope the audience got
absolutely fine, Diogo. My backstage indicates that we have no more questions from the field. In that case, I will say thank you gentlemen.
But it doesn't even make sense.
It was
to
my
have sushi.
pleasure,
And she does that with
again,
friends, too, right? It's like out of the gate.
and
That's-
hope to see you soon.
You know,
And
no,
just to
they were
mention,
not happy with her
we are back
organization.
in Munich in the
Stand
airport
on it.
Hilton
But-
in December. So
Think about that,
December will be the White Band Gap Conference back to Munich,
She said that, but yet she's
and
asked us to
we are
listen to
looking
six
forward
times.
to have a real event
Oh,
rather than a digital meeting on the screen. Thank you so much, making it a success, and looking forward to see you soon again. Goodbye.
Thank you, Bodo. See you in
Bye,
December.
everyone.
See you
See
in
you, Munich.
December.
Thanks, Bodo. Thank you, everyone. Thanks.